What's up? Look, I'll get to solving the problem in just about a moment. This is count the number of complete components. So, this is one of the problems from the most recently released competition batch. And it is quite exciting because it's an opportunity for me to solve an additional, a new, an interesting, an intriguing, and engaging graph problem. If you've been watching my channel for a while, you know that I love, absolutely adore, enamored by graph problems. As should you, because they are some of the most interesting, intuitive, fun data structure and algorithm problems to solve. And I'm just excited I have the opportunity to share the solution for this one with you guys. Anyways, with that said, let's go ahead and get right into the problem. Okay, so you're given an integer n. Sweet. Exactly what I wanted for Christmas. There is an undirected graph with n vertices numbered from 0 to n minus 1. Who's this hater who gave it a downvote? Like, you know, it's funny. Like, God could provide you, if you believe in God, the essence of the universe could provide you with $1 billion, eternal life, or whatever it is you wish for, and someone would still downvote it. They'd be like, nope. Because this is identical to that. This is essentially $1 million provided by Leetcode gods. Okay, there's an undirected graph with n vertices numbered from 0 to n minus 1. Okay, so might as well just write it down. We are given, what are we given? We are given n vertices. Okay, so there's a system with n vertices. A vertice, right, is just a node. So there's n nodes in this system. Numbered from 0 to n minus 1. Okay. And you're given a 2D integer array edges where edges of I equals AIBI. So what does that mean? So you're given a bunch of nodes and then you're given the edges between nodes, right? You're given the connections between nodes. Denotes that there exists an undirected edge connecting vertices AI and BI. Okay, so it's an undirected graph given all edges and the graph is undirected. Okay, and an actual problem solving technical interview context may not be worth it to write this information down, but since we're just going through the solution, maybe it'll be useful to say, okay, what are things that I'm going to be bullet pointing within my brain? What am I going to think about? Okay, there's n vertices, I'm given the edges, and the graph is undirected, okay? Those are the kind of the facts about the nature of this graph that I'm dealing with, right? I know that there's n vertices in this graph. I know that the edges in the graph are going to be given to me and that the graph is undirected, right? So if there's a connection from U to V, there's also a connection from V to U, which is what undirected graphing means. If that's not some concept that you're familiar with, then you're probably not prepared or ready to solve a median problem. Okay, denotes return the number of complete connected components. Okay, so this is kind of throwing me for a spin, right? Because most of us, if we're dealing with graph problems, you know, if we've dealt with enough graph problems, we understand this notion of connected components, right? A connected component is what? That means that nodes that can connect to each other, they have a path to each other, right? You can think of like like islands, not islands. That's a terrible example, right? A connected component just means that for any node in that component, they can reach each other, right? They can follow some set of edges to get to each other. For example, I guess the easiest way to understand this is, you know, there are two connected components here, right? And that should be pretty intuitive, right? Well, you can say like, all right, this is one component, right? Even if you don't understand the notion, right? I said, hey, how many connected components are there here? You might be like, all right, well, there's one thing here and there's one thing here, right? And everything in here can communicate with one another and everything in here can communicate with one another, but they aren't connected to each other because there's no way for this guy to get to this guy. Okay. Pretty intuitive idea. So that's what a connected component is. But prior to solving this problem, I don't believe I ever had exposure to this notion of complete connected component. So let's learn about what that means. So a connected component, formally, right, a formal definition, is a subgraph of a graph in which there exists a path between any two vertices. So anybody can reach anybody within this component, and no vertex of the subgraph shares an edge with a vertex outside of the subgraph. So that basically means, you know, basically what it's saying is like, you know, when we looked at this example, now it's slightly different, but, you know, it's the same notion, right? there's two connected components here, right? But this final point is saying, well, if there's another connection here, right? Well, now that they're connected, it's going to change the number of connected components, right? Because now everybody can reach everybody because I just added this new red node, so now there's only one connected component. All right, so weird formal ways of stating things often introduce like these strange notions of like, why would you make that statement? But that statement really concisely encapsulates the notion of what it means to be a connected component. But also you can just think about it in terms of a few graphs, and maybe that visualization will be a little more helpful. Anyways, connected components. We know what they are. We should know what they are. Let's continue. So what is a complete connected component? Well, a connected component is said to be complete if there exists an edge between every pair of its vertices. Okay, so what that basically means is I'll draw a few connected components, and then we'll determine if they're complete, again, via this notion of just visually looking at it, right? So this is one such connected component. Here's another connected component. Here's another connected component. Here's another connected component. Another one. Okay, whatever. So these are all connected components, right? Because from one node, I can get to any other node. From this node, I can get to this node. From this node, I can get to any node in here, right? From any starting node, I can get to any ending node within this component, But what does it mean for it to be a complete connected component? Well, that means that there exists an edge between every pair of its vertices, okay? So that means I can choose any two vertices, and there has to be an edge between them, right? So if I choose this vertice and this vertice, there's an edge between them. Right? If I choose this vertice and this vertice, there's an edge between them. If I choose this vertice and this vertice, there's an edge between them. But if I choose this vertice and this vertice, there's no such edge between them. So it's a connected component, but it's not a complete connected component, right? Versus in this problem, for any two pair of vertices, there's an edge between them. So this is indeed a connected component. This is not. And then if you look at these other problems, although this has a lot of edges between nodes, there's no edge here connecting these two to each other, so this is not. And this one, kind of a base case, sort of, right? There's only two nodes, there's one edge between them, so we're good. I guess the simplest form, which can be kind of tricky, is a node by itself. A node by itself is technically a complete connected component based on the definition, right? Even if it's not intuitive, because, well, if there exists an edge between every pair of vertices. Well, there's only one vertice, so the only pair is itself. And is there a way to get from myself to myself? Yes. Via what edge? No edge. So this is technically speaking, this is a solution here. Okay. So you can kind of see that in order for it to be a complete connected component, it has to be connected first, but also there's an additional constraint where for any vertice within that connected component, they have to have a direct edge to one another. Okay, so this kind of makes the problem more difficult. If it was just connected components, many of us would have already memorized not a brute force, but just brute forcely memorize the solution to this and know exactly how they're supposed to approach this. But since there's just this additional constraint, it might throw you, through a little bit of a loop. So when I solve this problem, it's not always going to work, but usually just write out what you know how to do, right? Maybe because this, what am I trying to say? I guess the situation here is there's a complete connected component, right? But a complete connected component is like a special form, right? A more constrained version of a connected component. And many of us should know how to find connected components. So maybe it'll be fruitful. Maybe it'll be a conducive approach. It'd be worthwhile to first find, all right, well, how do we find connected components? And then after that, consider, okay, now that we have found connected components, how do we determine if they're complete, right? And if we split it up in that manner, then maybe we'll be able to solve this problem by just kind of, modularizing our work. Saying, okay, we're trying to find complete connected components. Well, I don't know exactly how to find complete connected components, but I have before found connected components. So let me find connected components first, and then from there I'll figure out what I have to do to determine whether or not they're complete, right? So there's kind of two ways that if we know how to find connected components, and if you don't, well then we'll walk through that anyways, but most of us who are doing, you know, competition problems, especially new medium problems, that's something that we've learned how to do. And if you don't, well, I'll teach you today. But, you know, try to split up the problem into things you do know and things you don't know, and hopefully you can just spend time solving what you do know, and then from there you can think about, you know, what you don't know. But modularize your work so it doesn't become overwhelming all at once, right? So there's kind of two things to this problem. Well, maybe let's first find all connected components, right? Because that's something that we can do, and many of us have done that before, so it should be pretty simple. And then 2, determine if a connected component is complete. So what does that basically mean? Well, in order for it to be a complete connected component, it has to first be a connected component, right? So let's first figure out how all the connected components, and then look at all the connected components and figure out if they're complete. This I already knew how to do when I did this problem first. This I had to think about after I did this first step. So modularize your work. It's almost always going to be ideal. The problem is what if finding all connected components wasn't the right approach? Well, now I'm going down this rabbit hole, right? I'm trying this, and then I would get to number 2 and realize, oh wait, in order to do number 2, number 1 isn't the right precursor step. So sometimes when you solve problems, if what I'm saying is convoluted, it just takes a leap of faith. Sometimes you just have to trust, like, okay, you know, I don't know exactly where I'm going. I'm kind of going into darkness here with some understanding, and I'm just hoping, right? There's some luck associated sometimes. You're just taking a leap of faith that this is the right approach. And if it's not, then you might not get the role, but that's why you interview again, right? It's a numbers game with technical interviews. Sometimes you get them, sometimes you don't. But if you have an idea and you think it makes sense and there's some aspect of that idea that you know how to do, then just follow your gut, right? And it kind of makes sense here, right? Because in order for something to be a complete connected component, it has to be a connected component anyways. So it kind of logically makes sense intuitively that I should find the connected components. Okay, I'm rambling. So how do we find all connected components? Well, let's look at an example and use that example to find all connected components. Okay, so let's do example 2 here. Now we have 1, 0, 2. So I'll write the graph in the diagram. Just notice that you would construct this graph somehow using these edges, and then we'll use a formal, very standard approach to doing so, of representing a graph. Okay. So in order to first find if something is a complete connected component, we must first determine whether it is a connected component. Okay. And the way in which you do that is maybe intuitive, I'm not sure, but the notion is, well, the way you find a connected component, right, since these are bi-directional, is anywhere I can reach from here, everything I can reach can connect to each other, right? It's kind of like spreading, I kind of think of it like spreading something like a plague, right? And everyone who's infected could have infected one another, if that makes sense. So what I'm basically saying is, I'm going to label a node blue, okay? And I'm going to keep labeling things blue until I run out of things to label, okay? So what happens is I label this thing blue. And then I label this thing blue. And then I go here and I say, okay, I've already labeled everything. Now I've run out of things to go. I've ran out of space to go here, right? So I stopped labeling things blue. So I said, okay, I labeled everything blue. That's one connected component. So next I'll choose a different color. And I'll start labeling everything green. So I'll start somewhere. I'll say, okay, let me start at, okay, well, let's go through this in order. Let's think about how we would do this in order. Let me add a little bit more formality to this. So what nodes do we have? We have node 0, we have node 1, we have node 2, 3, 4, and 5, okay? So what I'll do is I'll first start by trying to color node 0 blue. And I'll figure out everyone 0 is connected to by continuing to color neighbors of 0 and neighbors of neighbors and neighbors of neighbors and neighbors until I've exhausted everyone that I can color. So I go to 0 and I color it blue. And I say, okay, a connected component including 0 is everyone that 0 connects to, right? So I color them blue as well. But maybe it'll be more look like this. So I'll go to one of its neighbor and color him blue. And anyone my neighbor can connect to will also be someone I can connect to, right? If I can connect to you and you can connect to them, then we can all connect to each other. So I'll color he'll color one of his neighbors blue. And then my neighbor will connect to all of its neighbors and see if they can color in blue. So he'll try to connect to me, but since I'm already blue, he'll say, okay, you've already been colored. We're already associated with one another, so I'll just discard. And now all these elements are a part of the same group. So I just looked at 0, right? I started looking at 0. And then I'll say, okay, let me try 1. But I'll notice that I've already colored 1 blue. So I've already found a component associated with 1. And then I'll look at 2, and I'll say, all right, I've already found a component associated with 2. Then I'll look at 3 and I say, okay, 3 hasn't been colored yet. So 3 is a part of a new component. And I'll color that green. And then I'll start looking at 3 and I'll say, okay, 3, I'll color you green and all your neighbors. So then I go to one of its neighbors. It has no other neighbors, but now 5 is going to be green. Then I look at 3 and I look at one of its neighbors and it's 4. And now 4 is going to be green. And then I'm done. I've exhausted. I've looked at everyone I can. So I kind of spread this color like a plague to everybody I can connect to. And that means everyone I can connect to is a part of one component. Right? And then I try 4 and I say, okay, 4 has already been colored a part of somebody else. 5 has already been colored a part of somebody else. Right? And you can imagine if there was a 6 here or something. Right? And there's a 6 here, then there'd be a new 6, and that new 6 would get a new color or whatever. So that's the notion of coloring. So what did I do? Well, basically, I look at each node. I look at each node U, color U a unique color, and color all of U's neighbors that color recursively, meaning, I keep going through, and I spread it like a plague until I can't, and then I look at the next node and the next node and the next node. If that doesn't make sense, we'll just write it in code, and hopefully that'll be a little bit more helpful, because that is not the best pseudocode that I've written, but hopefully that notion makes sense, right? So what I'm trying to do basically is I'm going to have a node U, right? And a color that I'm going to color it, okay? And I'm going to say, well, what happened here, right? Right, within this problem, since there's a loop, right, when I color this node, I'm going to color this node next, but I don't want it to, continue on forever coloring. If a node has already been colored, then I don't want to color it again, right? I've already colored it, so that means I've already processed it, so I don't want to process it again, right? So I'd say, okay, if this thing has already been colored, right? If color of U is already colored, then we just return. We don't want to continue coloring it. If not, that means that the color, so if it already has a color, otherwise we're going to say, okay, the color of U equals this new color. And then what I'll do is I'll say, I'm going to look at all my neighbors, and all my neighbors will be the same color, right? Because if I'm a certain color, if I'm colored a certain color, then that means all my neighbors will be colored that same color because we're all a part of the same component, right? If I'm a color, then everyone I can connect to, they're going to be that same color because we can all connect to each other, right? I can connect to my neighbor on the left, I can connect to my neighbor on the right, and my neighbor on my left can connect to me, and then to my neighbor on the right, and all their neighbors can connect to me, and we can all connect to each other, right? So I spread this like a plague through the system, right? So then I'm going to say, okay, I'm going to look at each neighbor, V, in some graph we're going to create right now, and I'm going to say, all right, I'm going to color the neighbor that same color, right? And that neighbor is going to do the same thing, right? That neighbor will color all of its neighbors the same color, and then it'll spread through. So first, let's create this graph. So let's have a graph, and then we'll just use a default dict to make it easy, and then we'll represent all the neighbors of a node with a list of all of its neighbors, all right? So then we'll say for UV in graph, for UV in edges, that'll connect nodes to each other. We'll say, okay, the graph at U has a neighbor V. So this is basically saying when I index into this graph, right, when I say graph of U, that gives me the neighbors of U. So maybe we'll call this N for neighbors, okay? And I'll say N of U, append V. So now U has the neighbor V and V has the neighbor U, which makes sense because, you know, 0's neighbors are 1 and 2, but 1's neighbors are 0 and 2, right? So 1 is a neighbor of 0 and 0 is a neighbor of 1. All right. And then this color thing, we'll just call it C instead of color. And we'll say that the default color is 0. That way, if this is 0, that means it hasn't been colored yet. So this will not return true. And then it'll start coloring it. All right. And then we'll start with a starting color. We'll just call it color 1. So color, instead of coloring them colors, we'll just color them numbers, right? But it's the same idea, right? We're coloring it something unique. Before, you know, in the illustration, we colored it a unique color. Now we're just coloring it or labeling it a unique number. Okay. And then remember before here, right? We did is we looked at all the nodes and we determined if we could color it or not. So we said, we'll look at all the nodes in range n, right? Because there's n nodes. And we'll say, well, if the color of u equals 0, so that means it hasn't been colored yet, then let's color this node in all of its neighbor color, and then we'll increase the color by 1 to represent that there's a new color that we're now referencing. All right. So when we do this, let's go ahead and print C so we can see this works for this example. So in this example, we should see 3 colors, right? N of U, append V. What's the problem? I think you need to do that. I don't know what I'm doing. Because lambda list would return a list, and you'd have to do it twice. Yeah. Okay, so don't worry about that. That's just me writing bad syntax. So this is saying that 0, oh, it's not this example. Oops. So 0 is a part of component color 1. 1 is a part of component color 1, and 2 is a part of component color 1. So 0 is 1, 1 is 1, and 2 is 1. 3 is a part of component 2, 3 is a part of component 2, and 4 is a part of component 2. So it means that 3 and 4 share the same color 2. 0, 1, and 2 share the same color 1, and 5 has color 3. All right, because this is telling us the color of that element, right? So the color of this element is, so the color of 0 is 1, the color of 1 is 1, the color of 2 is 1. So the color of 0 is 1, 1, and 1. So these are all the same color. The color of 3 is 2. The color of 4 is 2. So the color of 3 is 2, 2. So these have the same color, 2, 2. And the color of 5 is 3 because that's its own element over here. So that tells you the connected components. And voila, look at that. There's 3 connected components, right? So how would we then group these connected components together? Well, what we could do is we could just say, well, we'll put all the elements with the same color in the same group, right? So we'll have connected components equals default dict list. And then what we'll do is we'll just say, well, we'll look at each element in range n, and we'll add it to its connected components. We'll say the connected component, U goes in the connected component with the color of U. Append U. And then if we print connected components, what we'll see now is that there's these 3 connected components, one that's 5, 0, 1, 2, and 3, 4. So there's the 0, 1, 2 connected component, there's the 3, 4 connected component, and the 5 connected component. Right, so basically what I did is I'll just take all of them if they have the same color, right? And then I'll put them within their connected component. Does that make sense? Hopefully. Hopefully this code, if you just read it, it becomes intuitive. But I'm basically saying, like, you know, you all have the same color, so you'll get grouped into the same thing. You all have the same color, so you'll get grouped in the same thing. You all have the same color, you get grouped in the same thing. And so now they're all separated into their respective colorings. Okay. So how do we know in this example, right, the output is 1 because, you know, there's 2 connected components, but only one of them is complete because only this one has it such that every node has a direct edge to every other node, right? The problem here is there isn't this edge here. There needs to be an edge connecting 5 to 4, right? And there is no such edge. So since there is no such edge, we can't what? We can't call this one complete, right? There's 2, but only one of them are complete. One of them is complete. So how do we go about determining for nodes whether they're complete? Well, in order for something to be complete, right? A node, right? If you have this connected component, all right? There's one node in this connected component, and has a connection to all the other nodes in the connected component, right? But the only way this connected component is complete is that if for every node, right, for every node, they have to have a direct connection. So that means that this node has to have a connection to every single other node within the connected component, right? It has to, because if there wasn't an edge, right, like if we set it like this, right, there's all these connected components together and we don't know about their connectivity. If there isn't a connection between these two nodes directly, then it's not it's not a complete connected component. So we say, okay, to address that, then we'll put a connection between them, right? And then I say, okay, well, now there's not a direct connection between these two, right? They're connected somehow through this system, but they're not directly connected. So then I have to connect them. So the only way this is going to work, that is for any node, it has to have all the other nodes as neighbors, right? So if there are n nodes in a connected component, each node has to have n minus 1 neighbors, right? There's 3 nodes in this connected component, so each node has to have 2 neighbors, right? Because if it didn't have 2 neighbors, then it doesn't have a direct connection to another node. It has a connection through some other set of nodes, but not directly, right? Here, each node has to have 2 neighbors in order for this to be completely connected. These things are connected to each other. This one has 2 neighbors, so it has a direct connection to all the other ones. But this one only has 1 neighbor. In order for it to be completely connected, it has to have a connection to all the other neighbors directly within the system. And how many other neighbors are there? N minus 1, right? So I guess succinctly to state this, right? Each node U must connect to all other nodes V in connected component. I like how I said, I'd say it more succinctly, and then I literally just wrote out a long thread of bogus. So we'll say, we'll do it in some math speak here. So we'll say for all nodes U in the connected component, U must have a connection to V for all nodes V in the connected component, right? So that must mean U has the length of the connected component minus 1 neighbors, right? Because it has to have a direct connection to all the other components. So it has to have a direct link to all the other components. So it has to be direct neighbors with all other components. So it has to be direct neighbors with all number of connected component elements minus 1, right? If there's 3 elements in the connected component, then any one node has to have 2 neighbors, right? There's 3 elements in this direct connected component, so any one node has to have 2 neighbors. This has 2 neighbors, but this only has 1 and this only has 1, so it's not. So basically, to solve this problem, we find the connected components, which we've already written the code for, and then we just look and say, do you have n minus 1 neighbors, right? Do you have a direct connection to all other nodes within the connected component, which is just the result of calculating, do you have n minus 1 neighbors? Okay. That was rough, man. Rough explanation by a bad tutor. Okay. So to do that, what we'll do is we'll do this in one line because we hate ourselves. So we'll look at each connected component. So we'll look at each connected component we'll look at each component in connected component dot values, right? Because we don't really care about the color, we just care about the elements that are connected, right? So we'll look at this component, 0, 1, 2, then 3, 4, then 5. And then we'll say, well, in order for it to be, what? In order for it to be a complete connected component, the number of neighbors for each element, right? So the number of neighbors for each element has to equal the length of the connected component minus 1, right? So it's basically saying that I have all these elements together. Well, then the number of neighbors for each element must be the length of the component minus 1, because it should have a direct connection to all other neighbors within that component, right? So I have to have a direct connection to all other neighbors. There's length of C minus 1 neighbors, so I better have length of C minus 1 neighbors. Okay? So again, I really like how that was stated, right? For me to have a direct connection to all the elements in the connected component, then I must have a direct connection to all neighbors in the directed component. I have length of C, there's length of C elements in the connected component. Subtracting me, that means I have length of C minus 1 neighbors. So in order for me to have a direct connection to length of C minus 1 neighbors, I better have length of C minus 1 neighbors in that neighbor array where we kept track of all my neighbors. Okay. I've just reiterated this point into the dirt. Okay, so that must be true for each element within the connected component. So basically saying it must be true for all elements that they have length of C minus 1 neighbors in order for it to sum, and I'll do that for all the connected components that I found. So this will give me all the connected components, and this will tell me if it's complete. And then I just sum them at the end. Okay. Cool. Let's see. So this code is really messy, but, I kind of did it in parts, so I could probably make it more succinct and, cut out a bunch of unnecessary stuff if I want to. So what's the time in the space? Okay, so we have n equals n, so there's n vertices. Let's call it nodes because I can't spell. And there's m edges. Okay, so m is the length of edges. So n equals n, I guess. And m equals the length of edges. All right. So for time, well, we run DFS. We look at all n nodes, and then we run DFS. But from DFS, we'll never visit a node more than once, right? Because after we visit the node, we color it, and we never have to visit it again. So we visit each node once, and then we use each edge once, right? We could use each edge twice, right? Because we could use an edge going in one direction and then back in the other direction, I guess. So we visit each edge once, and we use each node at most once. Okay, we use each node once, and we use each edge at most twice. So that would be big O of n plus m for at least this part, right? So I add all the edges, that takes m time. I look at all the nodes, that takes n plus m time. I look at all the nodes here, n time. I create this default list. I figured all the connected components. There could be at most n connected components, right? If all the nodes are just by themselves and there's no edges. And then I just look at each connected component and determine the length of the node. So, this takes constant time to find the length. That's just a saved value. We look at, we make a comparison to length of C, a saved value. We look at each element in the connected component for all connected components. So there's at most n elements in total, right? In one case, there could be n connected components where each n connected component has one element, right? If they're just all the elements are standalone, so that's n time. And the opposite side of the spectrum, right, there could be one connected component where all the elements are a part of it. So even though this kind of has like a for loop and a for loop, it will never exceed n elements that we're checking, right? Because their connected components is just some partition, right, some split of the n elements that the n vertices that we have, right? So that will take n time. So n time, n plus m time, n time, n plus m time, 2m time, whatever, all that just comes down to n plus m time. Wait, what about for space? Well, we have to create this neighbor array, right? And we'll create an instance for each vertice, so that'll take n space, and then we have to create a reference to all the neighbors, so that'll scale with the number of edges. And then same for connected components, right? For connected components, well, there could be at most n connected components. It's the same deal as before. I'm not going to reiterate the point, but basically same thing, has most as n. So for space, that's also big O of n plus m time. Okay. So that's it for this video, guys. I hope you have a great rest of your day. Peace out.